A lot of nomenclature, you're right. Huh? What is it? So you looked it up? So the Bible is compiled. Most of the time, if you don't speak somebody's language, you go through it and interpret. So that would be like, I don't understand Spanish. Okay. So if I talk to somebody that knows Spanish, it goes through a what? Interpreter. All of them has to be translated.
Oh, okay.
But we call those people interpreters. Oh. Okay. But the Bible was compiled, so what they do is they take the Bible that's in the original Greek and they convert it over, completely over to another book that I can read at my convenience. Okay. So, like if I'm using Logic Pro, which is a simulation for the Allen Bradley PLC, I never download that to a computer. So that program is interpreted. Because it never creates a true machine code program. It does it on the fly. A compiler takes a level in a program in one language and completely translates it over to the other. We still have the source code over here that we can go back. So every time you download to the PLC, if you click on that button up there, it says compiler or compile. So what it's doing is it's taking your high-level language program and converting it over to machine language, and that's all the PLC understands. The PLC has no idea what ladder logic is. It has no idea what structured text language is or instruction language. It has no idea because it goes through an application that does what? That completely compiles a program, but you still have the original source code. The only language this computer communicates is machine language. It's ones and zeros. All the instructions are ones and zeros. All their operands are ones and zeros. Everything is ones and zeros. It has no idea what English is. It has no idea what the decimal number system is. Everything has to be what? Zeros and ones. So if you do it on the fly, we call that we call that an interpreter. If we completely convert it over, we call that a compiler. So some PLCs, and we hadn't got ours working yet, has a simulator. So you can bring the program up and you can bring up a simulator, and that is interpreted. That's not compiled. It's never sent to the PLC. And you never have a true machine code program because it's done on the fly, right? You understand? So there's quite a bit of difference. So every program that we send to the PLC has to be compiled or uncompiled. So if I was to upload from that PLC a binary program, it's got to come into my WAD. It's got to come back into my ladder logic. So it's compiled too. It's translated from binary back over to ladder. So a simulator, I ain't got it running yet, but one of the CDs we have in there, besides for the TIA portal, is a simulator. So if I run that simulator, I'm not downloading to a PLC, so what is it going to do? It's going to interpret the program, right? Huh? It's never a true machine code program. Never a true machine code program. All it is just a little module. So you put this over here, it'll run this little machine code module, and then but it never creates a full program. So that's a good question. It's pretty important to know, especially because right up there, Allen Bradley don't do that, but Siemens, it says 7. That's what it says. If you want to send it to the PLC, it says compile it. And we can pre-compile it just to check for compilation errors. So just because it compiles okay does not mean there's no errors in the program. It just means everything's in the right syntax, right? That makes sense? We have people say that even in intro to PLCs. They'll say, well, I checked it for errors and it said it was okay, but then they used the wrong input. But see, so it was in the right syntax or written, the instructions were written correctly, but it wasn't. So compilers don't check mistakes. Don't check for syntax. They check for syntax. Okay, any more? So all high-level languages have to be translated to be run on a computer. But what's nice is this is why we can have the same program for an Android phone that we have for an iPhone. They write it in a high-level language and they just run it through a different compiler. You know, it'll compile the same program over to the codes that the iPhone uses. The processors that the iPhone uses are the processors that these other computers use, these other guys, which is pretty neat. So on Blackboard, there is a what?
I was reading and I skipped the line.
Oh.
And what I read was the active conversion. It's called compiling. For example, the Bible.
So you did skip quite a bit. Well, the Bible's been compiled a lot of times. Even different English translations. You know, we got a lot of different English translations of the Bible. So, yeah, Southern Baptists. I think most Southern Baptists still use the King James Version, all these and thous. So, on the Blackboard site, we have reference material. I didn't know exactly what to call this, but this is, I call it generic reference material. And this has the ASCII code chart and the number system, control symbols, ISO, PLCs that we use symbols. But down here, this is the data types that we have for the available for the TIA portal, or the S7, by the way. So this is the way we change our instructions. So the RSLogic 500 use a dot to specify a word. But here, this is what we do here. So we've been using I. Let me turn on the projector. Get to do that all the time. Vary our instructions a little bit to determine if we're using, so on inputs, if we use I, this is what they call Boolean. This is just simply a bit, right? And we could have up to 65,536 bits. If we wanted to specify bytes, instead of using I, we would use what? IB. That way you could input a whole byte. You could input a whole byte of inputs at the same time. We don't have, because Siemens is a German PLC. So odds are if we bought the Siemens portal in Germany, we'd use E instead. That makes sense.
I was just curious if that would work.
I don't know. You might. I don't know. I've never attempted that. It might. Well, you could. IW specifies a word. Now the problem is that you have to remember. You remember on this PLC, you are controlling the memory. So if you input a whole word, 16 bits of inputs, you have to remember that, right? You understand that. This doesn't come into play except when you start dealing with numbers and memory bytes. And then ID, if I use ID, this would be a double word, which would be 32 bits. So we could actually input 32 bits at one thing. We do that a lot when we're trying to input from like thumb wheel switches and stuff like that, where you have thumb wheel switches like to set the speed of a motor or something like that, or even imitation switches that you have on a lot of HMI panels now, where you have an up and down button that you can press the speed to line up or something like that. We read those in. So Q, if we use Q, that's Boolean, which would be a single bit, right? QB, we could output a whole byte of information at the same time. QW would be a whole word that we could send out to multiple bytes, and then QD would give us up to a double word, which is 32 bits, right? Right, okay. Over here on memory, which we're going to use that a lot, M, if we use M, that's Boolean, right? MB, we could actually play around with a whole byte of memory at the same time. MW, a whole word at one time, and of course, MD would give us a lot. We could actually update a double word. And these we're not going to deal with. Let's see. And then T, timers and counters. We could actually have 65,535 different timers in this thing if we have enough memory in our PLC. So you have to remember one of the things that is going to show y'all is, and this is the TIA portal. This has nothing to do with the version of TIA portal that we're running. And I think I explained this to you, is that if you had a full-blown version of the TIA portal, you would have a bunch of different CPUs that you can select. The only CPU that we have available to us is the 1200 series CPUs, because we got this dirt cheap, right? I think I told y'all we got the PLCs. Huh? Yeah. What do you mean? Yeah, I don't know. I've never used these instructions before, but you can see it follows the same one. Follows the same format. In function blocks, usually we don't worry about this because function blocks are automatically defined when we set up a new, when we set up a subroutine, when we set up a timer, then the function blocks are automatically defined. And I've never used the user-defined data types either. That would be interesting. Yeah, but it seems like that would be. But I don't know I don't know how you specify. This is the range that we have. So Boolean numbers, we only have a 0 and 1, right? You understand that? And we can specify up to 16 different words, 0 to 1. A byte, we can, is 8 bits, we can represent numbers from 0 to 255. A word we can do, how do we calculate that, by the way? The number of combinations we could represent with any numbered system. Y'all remember that? So the number of combinations is, you take whatever base you're dealing with, and then you raise it, so this would be the base, and then you raise it to the number of digits. So 8 bits, that would give us 2, that's base 2 to the 8, which would give us 256 numerical combinations. Now to calculate the biggest number, it would be base to the n minus 1, because this gives you the total number of combinations, and in computers everything starts with what? 0. So the largest number you could represent this would give us the largest number we could represent in that base. So that would be, so it says we're using 8 bits, that would be 2 to the 8th, which is equal to 256, minus 1, which means that the largest number we could represent would be 255. That makes sense? So that's where those came from. So it says, okay, what would be the address and range for 16 bits? Well, that's going to be 2. I mean, it's going to be 2 raised to 16, which is 65,536, minus 1, which means we could have addresses from 0 to 65,535. And that's where they come up with this number. So 2 to the 32nd, or a double word, would be 2 to the 32nd, which is 1,048,576 or something like that. And then, of course, minus 1, right? Everybody okay? Now, what gets us strange is when we start moving to, by the way, in Allen-Bradley, they referred to them as integers. Integers are signed numbers. And what happens in Allen-Bradley, in Siemens, they refer to them as unsigned numbers and signed numbers. So notice the range changes a little bit. So it says a signed integer. I could have numbers between these signed integer. These are 8 bits. Then we have an unsigned integer. These are 16 bits. Then we have an integer, which is 16 bits. And then we have unsigned double integer, which is 32 bits. And then we have a double integer, which would be signed. Can you notice something about the signed numbers and the unsigned numbers? Well, if I look at this, if I took 65,536 and divided it by 2, I would come up and get 32,768. Now, what computers use, and we'll talk about this a little bit, you don't really have to. Yeah. So what happens is that I've got to be able to represent signed numbers without a symbol that says plus and minus. So what we do is we sacrifice one of the bits to determine the sign of the number. So what we do is we sacrifice the most significant bit. If the most significant bit is a 1, then the number would be negative. If the most significant bit is a 0, then the number would be positive. So if you sacrifice your most significant bit, you lose half the combination. Now, it uses a method called 2's complement. And why it does this is it needs to be able to do math without a sign. So if you think about it, if I wanted to, we'll call this is referred to as 10's complement. So if I wanted to say 55 and I wanted to subtract from that 32, now what I have here is I have a sign, but I'm trying to do this without a sign. So what we can do is we can take this bottom number right here and I'm going to subtract it from 0 and I'm going to generate a bar. So what would I do? That would make this a 10, that would make this a 9, and that would make this a 10. And what would that give me? That would give me 78. Now, if I was to come over here and do this longhand, what would I come up and get? This would be 3, and this would be 2. That would be 23, right? So what I'm going to do now is I'm going to take 55, and I'm going to add 78 to it. So what's 8 plus 5? 13. Carry a 1. What's 7 plus 6? Huh? So something didn't come out right. Did we do this right?
It's just a look.
So something's not working out, guys. So we borrow from this, makes this a 9, right? Oh, I'm sorry. 7 minus 9 is not, what's this, should this be? 6, okay, there we go. So let's add it again. So let's add 6 plus 6. What would that be? 12 with a carry 1. I dropped the carry. So what was the answer we got up here? 23. What was the answer we got down here? 23. But we did it by addition. And this would be called 10's complement. So technically, the computer can't really subtract. All the computer can do is add. But it adds using what we call 2's complement. 2's complement would mean, so let's convert 55 into binary. How would we do that? How would I do 55 into binary? Let's use a calculator. Yeah, y'all can do it longhand, but let's use a calculator. So I'm going to switch my thing over to programmers, and I'm going to say 55. I'm going to convert that to binary. So that's going to be 110, 111. And we're going to do this in 8 bits. So this is 8-bit sign numbers, right? Okay. So 1, 2, 3, 4, 5, 1. And that's a positive number. So notice what I have up here. 0. Okay. And then I'm going to take 32. I'll put my calculator in decimal 32, which I could do that one in my head. But anyway, go to binary. It would be this guy right here, right? Well, it's a power of 2. 1, 2, 4, 8, 16, 32. So that'd be 1, 0, 0, 0. Let's write it over here first. Okay. Now what we did up here to get this negative number is we subtracted it from 0. Of course, I'm going to carry this out 2 more digits because we're dealing with 8 bits, right? Okay. Now this is something you don't have to remember. Now just watch this. We can subtract this number from 0. Okay. There are several methods we can do that, or we can do it another method. This is why they call it a 2's complement. Is what we would do is so I could subtract this from 0. Or another method we could do is we could invert everything, which technically that's called a 1's complement. And then we add 1 to that, and this would be called the 2's complement. So 1 plus 1 would be what? 0 with a carry 1, 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 1, 1. So this would be this represented in the 2's complement. But notice what happened. Now all of a sudden we got this as a 1, which indicates it's a negative number. I'm going to come up here and add these two if I did the conversion right. If I know how to do math, right? Then I'm going to ignore the carry. So what's 1 plus 1? I'm sorry, 1 plus 0. 1, 1 plus 1. 1 plus 0. 1 plus 0. 0 plus 0. 1 plus 0. 1 plus 1 is 0 with a carry 1. This would be 0 with a carry 1. This would be 0, and what do? Drop the carry. Now hopefully this comes up and gives us 23. So this is going to be 1, 2, 4, 8, 16 plus 7, which is what? 23. So this is the way the computer does math. It does it by something called 2's complement, which is pretty neat because it does subtraction by what? By addition. But notice what happens. All your negative numbers, so that means I can represent negative numbers. So what I would do to figure out the range, we know we have 256 combinations, right? I divide that by 2 because I'm splitting them between negative and positive numbers. What would that give me? 128, right? Understand that. So that means I can represent negative numbers from 1 to 28. I can represent positive numbers from to 100, positive 127. Why do we always have one less positive number than we have negative? Huh? Because 0 has no sign. 0 is not negative 0. So, but 0 takes up one of your positive combinations. So that's why that's how they come up with these ranges. So 16 bits, we would take 65,006 and we divide it by 2, and then we drop 1 off the positive. And that's where we came up with those ranges, right? So that means I can do, so 6 integers, which is 16 bits, I can have numbers between 32,768 and 32,767. Unsigned double integers, I can have numbers between 0 and 4,994,967,285, which should get just about any industry through what they need to do as far as numbers goes. And then if I divide that by 2, that's why we came up with that range that I have if I deal with unsigned double integers, right? That makes sense? Then we get into what real numbers. This is what Allen Bradley called floating point numbers. Siemens calls them real numbers, which is what they are. These are numbers that can be positive or negative, but they can also use scientific notation. So your real numbers, we could have signed real numbers between this range. But now it all of a sudden jumps up to what? Where we can equal exponents, right? Now the problem is, as soon as it jumps into, I don't know where the shift occurs, but as soon as it jumps into scientific notation, of course your numbers are not as accurate, right? You understand that? Time is kept in 32 bits. Your date is kept in 16 bits. Time of day, I don't know exactly. The time of day, I don't know what the difference between time and time of day is, but it's 32 bits. In time of the day long, I don't know what that is. That's 12 bytes. Undoubtedly, it takes us back to out to the millisecond, right? So this would be days, this would be hours, this would be the hours day, the hours second. Oh, looks like it does. So it is years. So it's years. So it goes back to 1970, right? It's set up all the way up to what? 2062. So how will y'all be in 2060? Rich won't be here. 2262. Yeah, Rich won't be here. And the ASCII character set is 8. So even though this guy is built in Germany, the predominant way of sending text is still the old 8-bit ASCII code. So time of day, time is hours, minutes, and
24 days a year.
so okay, that makes sense now. So you don't need to know, but all I want to know, you don't need to know whose complement is used. All you need to know is that when we jump into signed numbers, we're going to get 1/2 of the combinations, right? Because we sacrifice 1 bit for the what? For the sign. And then we always have one more negative number with the positive number because 0 eats up one of the positive numbers. Okay, so how are we doing on lab? Looks like until today, because we had 2 people that says they couldn't be here last Thursday. So, I don't know what to do, guys. So let's go ahead and go to lab. Y'all got any questions about what we're doing in lab? Are you okay? Any problems with the instructions? I think we looked at, yeah, timers. We got a bunch of timers on the process section. But to me, timers are easier to do than the 500. I need to look at timers on the 5000 because on the S7 software, you know, you just enter the time. You don't have to worry about that multiplier that we used on the 500. You know, and a lot of people, even in that class, will see 500 up there and they forget to take it through through that multiplier that you're supposed to go to. So, all right.